We've seen in previous videos several ways of describing light and their applications. The simplest model of light is the ray model, which could be used for analyzing image formation by optical instruments such as microscopes or telescopes. The wave model explains why we can see fringes in a double-slit experiment, and it explains why the resolution of an imaging system is fundamentally limited by the wavelength of the light. Describing light as a form of electromagnetic radiation explains why light can be polarized. We saw that for monochromatic light, the X and Y components can oscillate independently, with different amplitudes and phases. The complex amplitudes of the two field components can be described by a Jones factor, where the time dependence is omitted. Different Jones factors correspond to different states of polarization. 1,0 corresponds to horizontally polarized light, 0,1 corresponds to vertically polarized light, 1,1 corresponds to 45 degrees diagonally polarized light, and 1I corresponds to left circularly polarized light. Using quantum mechanics, we can describe light as discrete packets called photons. With this model, we can explain why different types of light have different photon counting statistics, and it tells us how we can overcome the shot noise limit by using quantum light. However, in this model we haven't yet taken into account the polarization of the photons. In the following, we will look at how to model the polarization of photons quantum mechanically, and how the polarization could be used for quantum computing. In summary, we will see that the polarization of a photon can be described as a two-level quantum system. The Jones factor that we know from the classical description of polarization can be straightforwardly interpreted as a two-dimensional quantum mechanical wave function. We can call the basis ket vectors h and v for horizontally and vertically polarized light. This is useful for if we want to keep track of what is happening physically. However, if we want to use photon polarization for quantum computation, it is more convenient to call the basis states 0 and 1. Note that this is just a relabeling of the factors. It doesn't make any difference for the physics. Once we know how the polarization of a single photon can be described, we can move on to describing the state of a system of multiple photons. Then we will see how we can perform quantum computations by manipulating multi-photon states. The main difference between classical computation and quantum computation is that the classical computer can only take in one input at a time and give one output at a time. A quantum computer, on the other hand, can take in a superposition of multiple states and apply an operation that affects all states simultaneously. Let's see how we can go from the classical description of polarization to a quantum mechanical description. To find information about the polarization of a light beam, we introduce a polarizer. In this case, let's choose the transmission axis along the horizontal direction. This means that if we send in horizontally polarized light, all the light is transmitted. If we send in vertically polarized light, all the light is blocked. If light is polarized at a 45-degree angle, then the amplitude is reduced by a factor 1 over square root 2, which means the intensity is reduced by a factor 1/2. Now let's think of what would happen in the quantum mechanical case. If we send in a single photon that is polarized at a 45-degree angle, then the transmitted intensity cannot drop by 50% as it would in the classical case. The photon has to be either completely transmitted or completely blocked, but we cannot have half a photon transmitted, because by definition a photon is the smallest quantity that light can come in. However, if we have many photons, so that the situation becomes more similar to the classical case, we can reduce the transmitted intensity by 50% by saying that each photon has a 50% probability of being transmitted. We can describe this quantum mechanically by describing the polarization state of a photon with a two-dimensional wave function. The basis states denote horizontal and vertical polarization, just like in the classical description with the Jones factor. Therefore, the coefficients of our quantum mechanical wave function are the same as the coefficients of the Jones factor. Recall that according to Born's rule, the squared modulus of a coefficient denotes the probability of a measurement outcome if a measurement is performed. So to find the probability that a photon is transmitted by a horizontally oriented polarizer, we project the wave function on the state of horizontal polarization and we take the squared modulus. For 45 degrees diagonally polarized light, we indeed find the expected transmission probability of 1/2. In general, if the Jones factor has coefficients alpha and beta, then classically the transmitted intensity is the squared modulus of alpha. And indeed, in the quantum mechanical description, we find that the transmission probability of a photon is also the squared modulus of alpha. So to summarize, the coefficients of the classical Jones vector that describe the state of polarization translate directly to the coefficients of the quantum mechanical wave function. The transmission probabilities for a certain orientation of a polarizer is found by projecting the wave function on the appropriate basis state and taking the squared modulus. So this quantum mechanical wave function has a well understood classical analog, namely the Jones vector. Therefore, it is convenient to use this analogy to better understand in what ways quantum mechanical wave functions are similar to or different from classical descriptions. When discussing quantum mechanics or quantum computing, it is often said that the special thing about quantum mechanics is that a particle can be in a superposition of states. We can write down the wave function of a quantum bit or qubit as the superposition of a 0 state and a 1 state. It is often said that this means that the qubit is 0 and 1 at the same time, because if you measure the qubit, the measurement result can be either 0 or 1, and there is no way to tell upfront what the outcome will be. However, we saw in the context of photon polarization that this superposition simply corresponds to a diagonally polarized photon, and that it may or may not be transmitted by a horizontally oriented polarizer. Does it therefore make sense to say that the photon is both horizontally and vertically polarized at the same time? Not really. The photon is simply diagonally polarized, and this could easily be verified by putting the polarizer in a diagonal orientation. In that case, the photon will always be transmitted, and there is no uncertainty whatsoever in the measurement. Superposition is a concept that is well known in classical wave mechanics as well. It means that if two different waves overlap, the total resulting wave is the sum of the two separate waves. Quantum mechanics part ways with classical wave mechanics when it comes to the act of measurement. In quantum mechanics, if you measure a wave function, the outcome is fundamentally probabilistic, and the wave function collapses in a way that depends on the measurement outcome. That is something we don't see in classical wave mechanics. Another point of attention is the phase of the coefficients of a wave function. Let's say a qubit is in an equal superposition of 0 and 1. If we want to experimentally determine the state of the qubit, we have to perform measurements in one way or another. So the only thing that we can physically access are the measurement probabilities, which are given by the squared modulus of the wave function coefficients. But if we can only physically access the modulus of the coefficients, then what is the physical meaning of the phase of a coefficient? For example, if we change 1 over square root 2 into minus 1 over square root 2, or I times 1 over square root 2, the measurement probabilities stay the same. So how are these states different physically? The answer is straightforward if we interpret these wave functions as photon polarization states. We see that the first state corresponds to 45 degrees diagonal polarization, the second state to minus 45 degrees diagonal polarization, and the third state to left circularly polarized light. So the physical difference between the states is clear, but how do we distinguish them using measurement outcomes? We can easily distinguish the states using a polarizer in the 45 degrees diagonal orientation. In this case, photons in state 1 will always be transmitted. Photons in state 2 will never be transmitted, and photons in state 3 will be transmitted half of the time. Mathematically, what we did was describing the states in a different basis. We first wrote them in a horizontal-vertical basis, but by rotating the polarizer, we can more conveniently describe the states in the plus 45 degrees minus 45 degrees basis. To apply this basis transformation, we first express the plus or minus 45 degrees vectors in terms of h and v vectors. Then, to find the coefficients of the wave functions, we take the inner product of the wave functions with the new basis vectors. Once we have expressed the wave functions in the new basis, we see that the phase of the coefficients in the old basis affect the modulus of the coefficients in the new basis. So in summary, the phases of the coefficients become relevant when we change the measurement basis. As a final comment, let's look at pure and mixed quantum states. In quantum computing, one major problem is quantum decoherence, which means that the state of the system cannot be described by a quantum wave function anymore. This may seem odd at first. We've always described quantum systems using wave functions, Why wouldn't we be able to do so anymore all of a sudden? But when we interpret the wave function as a polarization state, it actually makes sense. We can describe polarized light using a Jones vector, but not all light is fully polarized. Light can also be partially polarized or unpolarized. Classically, partial polarization is explained by assuming there are rapid phase fluctuations between the x and y components of the electric field. If these fluctuations are correlated, then the phase difference is fixed, and the polarization state is well defined, so we can describe the polarization state with a Jones vector or a quantum wave function. But the less correlated the fluctuations are, the less well defined the polarization state is. So it is the correlation between Ex and Ey that determine the degree of polarization. We can describe this mathematically by introducing an object called the coherency matrix. The diagonal elements indicate the intensities of the x and y components. In case of fully polarized light, the off-diagonal elements indicate the phase difference between the two field components. If the light is partially polarized, the off-diagonal elements give the correlation between the field components, which is a measure for the degree of polarization. For fully polarized light, the coherency matrix is given by the outer product of the Jones vector with itself. Similarly, in quantum mechanics, some systems cannot be described with a wave function. In that case, the system is a mixed state, and it has to be described with a density matrix. If the system can be described by a wave function, it is a pure state, and the density matrix is then given by the outer product of the wave function with itself. To summarize, in classical optics, a polarization state can be described with a Jones vector, while a two-level quantum state is described by a two-dimensional wave function. What classically would be a well-defined polarization state, we would call in quantum mechanics a pure state. A partially polarized state corresponds to a mixed state. The coherency matrix that in classical optics can be used to describe a partially polarized state corresponds in quantum mechanics to a density matrix. We have seen in a previous video that polarization states can be described by points in the Poincare sphere. Fully polarized states lie on the shell of the sphere, and the less polarized the state is, the closer it lies to the center of the sphere. The equivalent in quantum mechanics is called the Bloch sphere. We now know how to describe a two-level quantum system, which can serve as a quantum bit of information, or qubit. But if we want to perform quantum computations, we will need more than just a single qubit. So let's see how we can describe quantum systems consisting of multiple qubits, which we for now assume to be polarized photons. Let's say the first photon is in a state described by coefficients alpha and beta, and the second photon is in a state described by coefficients gamma and delta. We now want to describe the entire system of two photons using a single quantum wave function. This new wave function is given by what is called the tensor product of the two single photon wave functions. To see what this means, we can write down the product of the two states and expand it. What we now have is a four-dimensional vector, where each basis vector describes a polarization state of both photons. Now let's write the single photon states as column vectors. From the expanded tensor product, we can directly read what the column vector of the two-photon state looks like. Note that to order the entries of the vector, we interpret the photon states as binary numbers and put them in ascending order. We can remember how to take the tensor product as follows. Take the first entry of the first vector, multiply it with the second vector, and put it in the product vector. Then take the next entry of the first vector, multiply it with the second vector, and put it in the product vector. If we take the tensor product of higher dimensional vectors, it is straightforward to see how this procedure is generalized. So now we know how to take the tensor products of vectors and how we can use them to describe multiple subsystems as one larger overall system. Now suppose we want to apply some operations to the subsystems and describe them as a single operator acting on the overall system. To do this, we need to look at the tensor product of operators. Let's say we apply an operation u to the first photon and an operation w to the second photon. By writing out the tensor product of the two vectors, we know what the final total state should look like. If we write out the expression, we see a pattern emerge. In the top left, we have the entry U1 multiplied by the matrix W. In the top right, the entry U2 is multiplied by W. In the bottom left, we have U3 times W, and in the bottom right, there's U4 times W. So we can write down the operator acting on the complete system in a straightforward manner. Just like the tensor product of two vectors, the tensor product of two operators is found by taking each entry of the first matrix, multiplying it with the second matrix, and placing the result in the product operator. Now let's see what happens to the complete system if we perform a measurement on a subsystem. Let's say we measure the first photon and find it in state 0, that is, it's horizontally polarized. Then the state of the second photon is found by projecting the total state on the 0 state of the first photon. Similarly, if we measured the first photon and find it in state 1, so vertically polarized, then we find the state of the second photon by projecting the total state on the 1 state of the first photon. In this case, we find that no matter the outcome of the measurement on the first photon, the second photon will always end up in the same state. This makes sense because we defined the initial state of the total system as the tensor product of two completely independent subsystems. Just because we wrote down a different mathematical expression doesn't change the fact that the two subsystems are independent. But now let's write down another state that cannot be written as the tensor product of two independent states. Now if we measure the first photon to be 0, the second photon must also be 0. And if we measure the first photon to be 1, the second photon must also be 1. So if we were to measure the second photon, the outcome depends on the measurement outcome of the first photon. In other words, one would observe a correlation in the measurement outcomes. When this is the case, we say the two photons are not two independent objects with separate states anymore, but rather, they share a single entangled state. Unentangled states are known classically as well. Simply take two polarized light beams, each with their own Jones vector, and take the tensor product of the two vectors. Then you have an unentangled state that is the superposition of 4 2-bit states. But having an entangled state for two spatially separated particles is a quantum phenomenon. Let's look at some other examples. Consider the equal superposition of all 2-bit states. This is an unentangled state because you can factor it into two equal superpositions of 1-bit states. But now let's change 1 plus into a minus. It may look like a minor change, but if we now measure the first photon, we see that depending on the measurement outcome, the second photon is either plus 45 degrees diagonally polarized or minus 45 degrees diagonally polarized. So by introducing a minus sign, the state has become entangled. For the final example, consider once more the equal superposition of all 2-bit states. We can rewrite the coefficients and then change two of them slightly in such a way that their squares still add up to 1. Now we see once more that we have created an entangled state, since the state of the second photon depends on the measurement outcome of the first photon. However, the two states only differ slightly, so you wouldn't notice much of the entanglement. What this shows is that entanglement isn't a binary state, that two particles either are or aren't entangled, but rather there is a continuous spectrum, and one can speak of higher and lower degrees of entanglement. For our first example of quantum computation, we look at Grover's algorithm. Let's first understand the problem the algorithm tries to solve. Suppose we have a list of names, and the names are not sorted in any particular order, such as alphabetically. We can denote each entry with a number from 1 to 8, or, to more clearly see the relation with the qubit states, we can denote each entry with a binary number from 0 to 7. The problem that we're trying to solve is to find the number corresponding to a particular name on the list. Classically, the best we can do is go through the entries one by one. So first we check entry 0 to see if that's the name we want. If it isn't, then we try the next entry of the list, and we go on like this until we find the right name. So the number of function evaluations we need to perform can range anywhere from 1 to 7, depending on luck. Now we want to see whether we can do any better using quantum computation. The first thing we need to do is to define the following function. The input state is multiplied by -1 if it corresponds to the correct name. Otherwise, it remains unchanged. So if our input state is 0, 0, 0, then the output state is also 0, 0, 0. The same goes for the other states except state 1, 0, 0, for which the function will return minus 1, 0, 0. Now comes the trick. Instead of trying one state at a time, we create as input a superposition of all states. After evaluating the function only once, the output state already contains the information about which state is the correct state. However, we cannot extract that information from the output state as it is currently. If we were to measure this state, the outcome could be any random state with equal probability. So we need to perform some extra steps. More specifically, we need to manipulate the wave function so that the coefficient for the 1, 0, 0 state has a high magnitude. That would mean that if we perform a measurement, we would find the correct state 1, 0, 0 with high probability. To do this, we introduce an operation that involves inverting around the mean. We can plot the coefficients of the wave function and indicate the mean value in the plot. To invert around this mean, we subtract the mean, flip the sign of all the coefficients, and add back the mean. We see that by applying this operation, the coefficient for the 1, 0, 0 state now indeed has a higher magnitude. Just to verify whether this operation is indeed a valid quantum operation, we can add the squares of all coefficients to see that indeed they still add up to 1. Now let's repeat what we've done, but now we also write down the mathematics. The first thing we did was generating an equal superposition of all states. We can write this as a column vector. Then we flip the sign of the entry we're looking for. We can write this as a matrix operation, which we call U omega. This operator is also known as the oracle, because it contains the answer to our problem, but we don't know a priori what this operator actually does. The next step was to invert around the mean. First, we compute the mean, which can be done by taking an inner product. By defining the vector S, we can write the inner product more concisely. To obtain a vector filled with the mean value mu, we can multiply mu by the vector S. Now that we have calculated the mean, we can subtract it from the wave function. Then we flip the sign, and then we add back the mean again. Now we can write the inversion around the mean compactly as an operator US, which is also called the Grover diffusion operator. So now we have found two operators, one that evaluates the list of names, and one that inverts the wave function around the mean. Grover's algorithm can then be written as follows. We start with a wave function that is the equal superposition of all entries, and then we repeatedly apply the Grover iteration, which is composed of the oracle operator followed by the diffusion operator. We need to keep iterating until the magnitude of the coefficient of the correct entry is maximal. If we then measure the wave function, we will find the correct entry with high probability. The number of required iterations depends on the length of the list. If we have 3 qubits, then the list is 2 to the power 3 equals 8 entries long. If the list has n entries, then it can be shown the algorithm requires of the order of square root n iterations. So if the list has 1,000,000 entries, then using quantum computation, we require only 1,000 evaluations of the list, whereas classically, we could require up to 1,000,000 evaluations. Now let's think a bit more about how quantum mechanics helped speeding up the solution to the problem. We started with a wave function that is a superposition of all inputs. While this is an important step in the quantum algorithm, generating the superposition is not something inherently quantum mechanical. If you have two diagonally polarized classical light beams and want to describe them using a single vector, you also get an equal superposition of all states. The quantum mechanics comes in when we check the list and flip the sign of one entry. When we do this, we create entanglement between the two photons. As we invert around the mean and apply more iterations, the state keeps being entangled. For our second example of quantum computation, we look at Shor's algorithm. The problem we're trying to solve here is factoring a large number n. So if n is the product of two prime numbers p and q, we need to find p and q while we only know n. To solve the problem, we take the following steps. First, we reformulate the problem. This step is completely unrelated to physics or quantum mechanics. It is purely mathematical. By applying some mathematical theorems, we can demonstrate that we can find the factors of n by generating a series of numbers and then finding the period of that series. Then, quantum computing is used to find the period of the series more efficiently. Classically, we only compute one number at a time until we find some repetition. But quantum mechanically, we can evaluate the entire series in one go. The problem then is that even though the relevant information is present in the quantum wave function, we cannot extract it yet by performing a measurement. Rather, we first have to apply a quantum Fourier transform to the wave function, and then we can perform a measurement that reveals the period of the series. So, let's see how we can reformulate the problem. As an example, let's take n equals 209, which has as prime factors 11 and 19, which we aim to find. What we need to do is pick some random number a. In our example, let's pick a equals 12. Now we're going to create a series of numbers where the kth number is given by a to the power k modulo n. What this means is that we raise a to the power k and calculate the remainder if we divide it by n. Let's calculate this series for several k. For k equals 0, we get 1. Then we get 12, 144, 56, 45, 122, and then 1 again. If we were to continue this series, we would find the numbers repeat themselves with a period of 6. Let's prove that indeed the series is periodic, and the period is given by that k for which a to the power k mod n equals 1. The periodicity of the series follows from the observation that the value of sk determines the value of sk plus 1, which we will now demonstrate. If we know sk, then sk plus 1 is given by a times sk mod n. This is because sk is the remainder of a to the power k divided by n, which means there is some integer m such that a to the power k equals n times m plus sk. To calculate a to the power k plus 1, we multiply both sides by a. By definition, sk plus 1 is given by the remainder of a to the power k plus 1 divided by n. If we substitute our expression for a to the power k plus 1, we can eliminate any multiples of n, since they don't affect the remainder. We then find what we were trying to prove, namely that sk plus 1 is directly determined by sk. What this means is that if S6 equals S0, then S7 must equal S1, because the previous numbers are the same. But if S7 equals S1, then S8 must equal S2, because their previous numbers are the same. We can keep continuing this argument indefinitely, from which it follows that if a certain number appears twice in the series, it must appear periodically. In particular, we know that for any a and any n, S0 must always be 1. So if r is such that Sr equals 1, then the series must be periodic with period r. Now the question is, how is this knowledge going to help us in finding the prime factors of n? We now know that if the series is periodic with period r, then a to the power r mod n must equal 1. We can subtract 1 from both sides and then factorize the expression. This equation says the number on the left has a remainder of 0 when divided by n, which means it must equal some integer m times n. We furthermore know that n equals p times q, which are the two numbers we are trying to find. For the sake of notation, let's call a to the power r over 2 plus 1 a, and let's call a to the power r over 2 minus 1 b. If r is an even number, then a and b are integers. R will not always be an even number, but let's assume that we're lucky enough so that it is even. In our example, r equals 6, so indeed it is even. Now we have to be lucky a second time and assume that neither a nor b are multiples of n. If indeed they are not, a must contain one prime factor of n, and b must contain the other prime factor of n. If these expressions for a and b are valid, then it follows that the largest number that divides both a and n is p, and the largest number that divides both b and n is q. In other words, the greatest common divisor, or GCD, of a and n is p, and the GCD of b and n is q. The GCD of a pair of numbers can be found straightforwardly by using the Euclidean algorithm, which works as follows. If we want to find the greatest common divisor of 1729 and 209, we first calculate that 1729 mod 209 equals 57. Then we claim that the GCD of 1729 and 209 equals the GCD of 209 and 57. Let's demonstrate that this is indeed the case. The fact that 1729 mod 209 equals 57 means that 1729 equals some integer times 209 plus 57. Now let k be the greatest common divisor of 1729 and 209. That means that 1729 equals some integer times k, and 209 equals some other integer times k, and these two integers cannot share any common factors. By rewriting the equation, we see that k must also be a divisor of 57. So k divides both 57 and 209. Furthermore, we can demonstrate that m minus 8n shares no common factors with n. To see that this is true, let's assume the opposite, namely that they do share a common factor f. That means that dividing the numbers by f gives two integers, and because a times n over f is an integer, then m over f must be an integer as well. But that means that m and n share the common factor f, which contradicts our earlier assumption that m and n share no common factors. Therefore, indeed m minus 8n shares no common factors with n. And from that it follows that the greatest common divisor of 209 and 57 equals k, which was assumed to be the greatest common divisor of 1729 and 209. So we see that indeed the GCD of 209 and 57 equals the GCD of 1729 and 209. We can repeat this logic to find it is also equal to the GCD of 57 and 38, which is equal to the GCD of 38 and 19, which is 19, and indeed 19 was one of the prime factors which we were trying to find. So let's summarize how we reformulated the factorization problem. We picked some random number a. We calculated the series a to the power k mod n and found the period r of that series. Then, using a and r, we calculated a new number, a to the power r over 2 plus or minus 1, and the greatest common divisor of this new number and n yields with decent probability a prime factor of n. So far, we have only done mathematics and no physics or quantum mechanics whatsoever. The quantum mechanics comes in useful when we want to find the period of the series. Classically, we must compute the series one number at a time, but with quantum computing, we can do it more efficiently. So let's see how we can efficiently find the period of the series using quantum computing. We need to introduce two registers of qubits. For our example, let's say that the registers are 10 qubits large. We set the first register to be in a maximal superposition of all 1024 states, and we set the second register to be in the ground state. Note that technically, these quantum states should be normalized so that the squares of all coefficients add up to 1, but for the ease of notation, we will omit this normalization constant. We can relabel the states by converting the binary numbers to decimal numbers. So we have two registers, one in a state of maximal superposition, the other in the ground state. We can write down the wave function of the entire system by taking the tensor product of the wave functions of the two registers. Now we need to apply modular exponentiation to all the states of the superposition. When we apply this to one particular term of the superposition, the state of the first register remains unchanged, while the second register is mapped to a to the power k mod n. If we consider again our example of n equals 209 and a equals 12, we find a wave function where the labels of the states of the first register go from 0 to 1023, and the labels of the state of the second register repeat with a period of 6. So we see that the wave function already contains the information we want to find, namely the period of the series. Now we need to manipulate the state such that we can extract this information. To do this, we first apply a measurement to register 2. We will get one of 6 possible outcomes, and depending on the measurement outcome, register 1 will collapse to a certain state. For example, if we measure register 2 to be in state 1, register 1 collapses to the series 0, 6, 12, etc. If we measure register 2 to be in state 12, register 1 collapses to the series 1, 7, 13, etc. And the same goes for the other possible measurement outcomes. But whatever the measurement outcome for register 2, we know with certainty that register 1 will collapse to a superposition of states whose labels have interval 6. Let's assume that we measured register 2 to be in state 144. Then register 1 collapsed to the superposition of 2, 8, 12, etc. We see that register 1 contains information about the period that we try to find, but we still cannot extract it with a straightforward measurement. If we were to measure register 1, we would get one random number from the superposition, say 62, and then all we have calculated is that 8 to the power 62 mod n equals 144. Instead, we have to do something extra. We have to apply a quantum Fourier transform to register 1. For functions of a continuous variable x, the Fourier transform is very effective in finding periods. For example, if a function f of x consists of a series of delta peaks that are a period r apart from each other, then the Fourier transform of f of x yields a series of delta peaks with a period 1 over r apart from each other. So the position of a delta peak in f hat of omega gives information about the period of f of x. So if we could apply some sort of Fourier transform to the wave function of register 1, we would get a wave function that we could measure to directly get information about the period r. So ideally, if we applied some sort of Fourier transform to the wave function of register 1, we would get a wave function that is a superposition of 0 over 6, 1 over 6, 2 over 6, etc. But what would a state with label 5 over 6 physically mean in terms of the 10 qubits that you measure? In the end, you measure a sequence of 10 zeros and ones, which you can interpret as a binary number, and then convert to a decimal integer number. How would you interpret such an integer number as a fraction like 5 over 6? To find out, let's look in more detail at what it means to take a quantum Fourier transform of the wave function of register 1. Let's denote the wave function as psi, and its quantum Fourier transform as psi hat. The coefficients of psi and psi hat are related by a discrete Fourier transform. If we compare this to the expression of the Fourier transform of a function of a continuous variable, we find that the continuous Fourier variable omega is analogous to the discrete Fourier variable k prime over k. So if we apply a quantum Fourier transform to register 1, measure the resulting wave function, and find a value of 853, we can interpret that value as the Fourier variable being approximately 853 over 1024. So we know that ideally, the quantum Fourier transform of register 1 should peak at multiples of 1 over 6, but in practice it is only defined at multiples of 1 over 1024. Since 1 over 6, 2 over 6, 4 over 6, and 5 over 6 cannot be expressed as integer multiples of 1 over 1024, the amplitude leaks out to adjacent states. If we now measure register 1, there is still a probability that we obtain a useless outcome, such as 0 or a number where the amplitude has leaked into. But let's suppose we measure a useful outcome, such as 853 over 1024. How do we find out that 853 over 1024 is supposed to approximate 5 over 6? The way to find out is by using continued fractions to obtain increasingly more accurate approximations of 853 over 1024. We can check for each of these approximations whether it solves our factorization problem. So let's see how we find approximations from continued fractions. We start with 1024 over 853 and split off the integer part, which is 1. We rewrite the remaining fraction as 1 divided by its reciprocal. Then we again split off the integer part, which is 4, and rewrite the remaining fraction as 1 divided by its reciprocal. And then we can repeat this step again. To find approximations of 1024 over 853, we can truncate this sequence at different points. If we truncate it at the first step, we find the approximation 1. If we truncate it at the second step, we find the approximation 5/4. If we truncate it at the third step, we find the approximation 6/5, and it is this approximation that we were looking for. This completes the explanation of all the steps of Shor's algorithm. To summarize, we want to find the prime factors of n. To do this, we pick a random number a, which we use to generate a series of numbers. We find the period of this series using quantum computation. This is done by introducing two qubit registers. The first one is in a maximal superposition of all states, while the second one is in the ground state. We apply modular exponentiation to the second register, and then measure the second register so that the first register collapses to a superposition of states whose interval is the period r. By applying a quantum Fourier transform, and then measuring register 1, we find an approximation of a multiple of 1/r. To find r from this approximation, we use continued fractions. Once we successfully find r, we find the prime factors of n by computing the greatest common divisor of a to the power r/2 plus or minus 1 and n using the Euclidean algorithm. It is important to note that Shor's algorithm doesn't guarantee to always successfully return the correct prime factor, but it does so with a decent probability, and because the algorithm is computationally efficient, it is acceptable to run the algorithm several times until you get the correct outcome.